People seem cold. Is it cold outside? Okay. Okay, so we are nearing the end of the semester. We're already at lecture 23. Oh, that's a lot of lectures. We've covered a lot of concepts. Today we're going to cover some more. I'm going to focus on on-chip networks today, but I'd like people to think about communication substrates in general. We talked a lot about memory in the early lectures, and then we talked about some approaches to tolerating and hiding memory latency. And then we started talking about communication last week, which is really part of memory. Memory and interconnect are very tightly integrated. And these are really big source of latency and energy in our systems. And going forward, I think this, not only memory needs to change, but also interconnect needs to change. And together, I think they need to change significantly to really satisfy the needs of workloads. We discussed it a little bit last time, but we're going to discuss it a little bit more. Okay. So this is just a recall slide, just to jog your memory. We've talked about interconnection network basics. We covered a lot of topologies. We discussed routing algorithms. And we discussed buffering and flow control. Keep that in mind. And there were many design decisions over here. And these are actually quite interesting, I think. In the end, a lot of these can be coupled with each other, as we have also discussed. And we talked about buffered flow control. And this is actually what people have been thinking about for a long time. Today, we're going to kind of deconstruct buffered flow control, where you're going to try to get rid of buffers as much as possible. Again, this is another review slide. You've seen a lot of this. We looked at how to do the buffering, what to buffer, and how to do the forwarding, etc. We talked about store and forward, wormhole, and then we talked about using virtual channels, because it doesn't make sense to block some of the packets that are going on routes that are really not contended. And you've seen this picture before, so I'm not going to go through this in detail. But virtual channels enable you to not block packets unnecessarily because you have FIFO queuing. So it's a tweak on FIFO queuing, in a sense. You have multiple FIFOs, and you can select from different FIFOs. So you can think of in-order scheduling, which is FIFO, and then completely out-of-order scheduling. You have to examine every single thing in your entire buffer to decide which packet can be scheduled to which destination, which port. Virtual channels give you complexity closer to FIFO, away from the out-of-order, by getting some of the benefits of out-of-order scheduling. So in DDCA, for example, we've covered out-of-order execution, right? You have in-order execution of instructions, which is terrible for latency tolerance. You have completely out-of-order execution of instructions, which is bad for complexity, but good for performance. Think of virtual channels as a way of achieving part of the out-of-order scheduling benefits without having complexity commensurate with out-of-order scheduling. In processor cores, we're actually very used to out-of-order scheduling of instructions, right? In networks, maybe we're less used to out-of-order scheduling of packets, but it's good to think about that going into the future. Okay, so that's virtual channels. These were we discussed last time. And then we also discussed how to communicate buffer availability. This is an interesting issue because you have really a network. And if you want to send a packet to some other node downstream, you need to know whether the buffer is available, right? And there are different ways of doing this, and we discussed those different ways. All of them add complexity in the end. And this is one of the complexities that we actually wanted to get rid of with some of the networking design choices that we're going to discuss in this lecture. All this sounds good? No questions on these topics? We've covered this in the last lecture. We also talked about interconnection network performance. I'll go through this a little bit because I think this is important. This is a really fundamental curve. Essentially, it's called a load latency curve. Load is really the x-axis, which could be measured in different ways, but one way of measuring it is to measure the injection rate into the network. This is the rate of packets that go into the network every second, let's say, or every clock cycle. Or the other way of thinking about it is the amount of load on the network. You can think of network as having a capacity, which is the load that it can bear. And 100% means every single capacity in the network is kind of utilized, maybe. And what happens, this curve shows what happens to the latency, which could be measured in different ways also. This could be the average latency of a packet from a source to the destination, right? It could be the maximum latency also. But essentially, this curve shows the effect of the amount of load injected into the network on the latency. And this is a very fundamental figure. Clearly, you can draw this for synthetic patterns, as we have discussed last time. But before I go into that, I should say that these are really determined by the latency you get for a given access pattern, for a given injection rate, is really determined by all of the design choices that we discussed. So you have some minimum latency given by topology. So if your topology is, for example, point-to-point, where every node is connected to every other node, that latency is probably the minimum latency you will ever get. Of course, you have a lot of complexity because you have dedicated wiring between every single point, every single node in the network. But of course, if your topology is something totally different, a mesh topology, for example, two-dimensional mesh, then you need to go through multiple hops to reach your destination, assuming that source and destination are far from each other. Right? So this is what I mean by minimum latency is given by topology. On top of that, you need to do routing on a topology. Topology by itself doesn't mean anything. You need to do routing to actually make use of the topology, right? You need to get from source X to destination Y. And there are many different routing algorithms you can use. And different routing algorithms have different minimum latencies. And they behave differently at different injection rates for a given topology. So it's good to think about that. So there's some minimum over there, and there's some complexity in the routing algorithm. You need to make the decision, so it takes time to actually do the routing. On top of that, you have flow control and buffering that affects your minimum latency. Because yes, you do the routing, but they affect the design choices that you make for whether you have buffers or not, how big your buffers are, what is your flow control mechanism. They all affect the latency of when you can send the packet, when you can buffer the packet, when you need to stall. And as a result, that also affects your minimum latency. And these effects can be different at different injection rates also, depending on the efficiency and the scalability of your algorithm. And that's what gets us to zero load latency. So this asymptote over here on the y-axis really gives you the zero load latency. If you don't have any load on the network, over here basically, what is the minimum latency that you can get? Of course, as you keep adding more, as you keep injecting things, you get more latency. Okay, so you can do the similar. You can do the same thing on the other side, which is what is the injection rate? The maximum injection rate you can have in a network is really determined by your topology. Your topology basically tells you this is how much your network can. How much load your network can carry, and it can still deliver packets, right? Clearly, this curve doesn't extend all the way over here, meaning this particular network for a given pattern cannot have this injection rate, cannot sustain that injection rate. Okay. Also, your routing has some inefficiency, which means that it affects your throughput. I'm going to name this as saturation throughput, basically over here. It really affects how much load your network can sustain because of the inefficiencies it has. And also on top of that, buffering and flow control has some inefficiencies that reduce your throughput. So you can see that on the y-axis, we've added more latency based on our design choices. On the x-axis, we've also reduced the injection rate based on our design choices. Then the question is, what is this curve, right? Basically, here you have the zero load latency. Here you have the saturation throughput, meaning the throughput at which the network cannot really function, beyond which it cannot function, or latency shoots up. And this curve can be essentially plotted for different types of access patterns, for different types of design choices. Okay, I've already discussed this. So I'm going to skip these because we already discussed it, but ideal latency, you cannot achieve it because you have this is really the latency due to wire delay between source and destination. Clearly, we don't have just wire delay between source and destination, right? What I just discussed over here, all of these add things beyond the wire delay, right? Even if you have a point-to-point topology, you have things beyond the wire delay, right? You have to send the packet and receive the packet, right? At the very least. And you have to figure out which destination to send the packet also, right? Because you have a lot of connections to everybody else. Okay, so because dedicated wiring is completely impractical and also controlling it with zero latency is impractical, you really segment the wires by inserting routers, and also you have additional overheads. So that brings us to the load latency curve over here. Ideally, basically, you should get something that looks like this. But really, in workloads, this is what we get. And this curve really depends on what kind of communication pattern you have. I will not go through this in detail. You will see a lot of examples that look like this in many network papers, where we look at different types of traffic, and we look at the latency, load latency curves for different types of traffic, for different, in this particular case, different topologies with some particular buffering and flow control and routing choices, right? So all of those affect you. So for example, if someone gives you a curve like this and tells you, these are my topologies, and I pick some, let's say, pattern, uniform random traffic. This means that any node can send, can be a source, and it uniformly and randomly sends a packet to any other node in the network. And the probability of the communication between any given source and destination is equal. That's the definition of a uniform random traffic. If someone tells you, this is my traffic pattern, these are my topologies, and these are the curves I get, then the first question you probably should ask is, okay, this doesn't tell me anything. You basically say, what is the routing? What kind of routing decisions have you made? What kind of buffering decisions have you made? What kind of flow control decisions have you made? Because all of those really affect this curve in the end. You may have a not so great topology in terms of connectivity, but you may do extremely well in routing and flow control, for example, and that topology may outperform a very well-connected topology. Ideally, it should not. That means that you're probably not doing a good job in how you are doing routing and also flow control in your well-connected topology. So this is just to give you an idea that you need to question all of these numbers. And also, these are synthetic traffic patterns. If you look at this, these are not applications. And we're going to talk a lot about applications today. These synthetic traffic patterns are interesting to understand the different design choices you may make and how that affects essentially this load latency curve for different type of synthetic patterns that you can perhaps understand better. But this may not tell you anything about how an application will perform, as we will see soon. Does that make sense? Because an application is really not a synthetic pattern in the end. Very few applications do purely uniform random traffic. Very few applications do purely, let's say, I don't know, here we have bit complement traffic. Basically, it's an access pattern where you complement IJ and source and destination are IJ and source is IJ and the destination is kind of JI, something like that. I may have gotten the definition completely wrong because people define these things. But these are very synthetic patterns, as you can see, right? It really depends on what the application is doing, the curve you get. So these are some of the topologies that we've examined in the prior slide. If we have time, I'll get back to this. But I think you've seen part of it, right, from the last lecture? Okay, good. I'm still covering stuff from last lecture a little bit. But I think it's good to examine topologies more and more so that we can understand better topologies. And we've done some of that. I'm not going to talk about that in this lecture. And there's also other things that you can do. If you have time, I'm going to get to this today. Any questions? By the way, load latency curve is quite general, right? It's actually not a function of a network, not just networks, or you could consider everything as a network. That's another thinking that you have. Everything, like including us, human beings are networks. If you put more load on a human being, you'll get more latency, right? Meaning if you send more emails, at some point you'll get longer response times, right? And at some point you get a saturation throughput. None of the emails may get any response, right? So that's very fundamental, right? Okay, so network performance metrics, we've discussed this a little bit last time. I'm not going to talk about this. Today, we're going to focus a lot on application level performance. In the end, what really matters is the application you're executing. And application level performance could be clearly execution time if you're executing a single application, or a job throughput if you're executing many applications. And clearly, both of these could be affected by interference among different threads and applications. And we're going to see some of that today. But before I go into some of the more specifics, I think I will mention what I said earlier. I think we really need to rethink how we design communication networks going into the future, because a lot of things are changing. And they already changed, actually, but more changes to come. Clearly, we're having new architectures, new applications, and new technologies, and they all demand revisiting, rethinking how we actually handle communication. And I believe we're not doing enough of that in the design of our systems. So we're going to talk about on-chip networks a lot today. versus off-chip. So some of that rethinking is I'm going to show you with examples. Clearly, there's communication that happens between on-chip units that is a bit different from communication that happens between off-chip units in a supercomputer, for example. Then we discussed a lot about processing in memory and storage in this course, right? And we talked about, for example, connectivity within the DRAM. There's more to do over here, basically. If you have actually a lot of processing on the memory side, you need more connectivity across the processors as well. And I think this is going to be more important in the future. There should be more communication between in-memory processors. There should be more communication between memory-centric and compute-centric units between the processing and memory system as well as the other accelerators in the system. And I think this requires more rethinking. And some of the actually work that's going on in architecture conference these days target this, which is good, but there needs to be more. At the same time, we have new and evolving workloads, which are demanding changes both at different levels of networks. So clearly, machine learning, for example, is a very data-intensive workload. Genomics is another one. We're disaggregating our systems more and more, right? You actually have, essentially, if you look at a data center today, you're really distributing computation and memory and storage across the entire data center. So you really need to rethink how you handle communication between those units. If you have, for example, disaggregated storage, disaggregated memory, where a lot of the memory and storage sits far away from where computation is done, then you may actually need to rethink how you do the communication across those. And within that disaggregated system, you may actually have computation also inside the disaggregated storage or memory. So there's a lot to do over here. And on top of this, I think we have new technologies. By the way, are these the latest slides? They don't seem to have what I added over here. It tripped my, maybe I sent you the, okay, there's the optical wireless chiplets. Let me see. I'll do the CRC check. Oh no, what happened here? I can see myself. It has 295 slides. It's supposed to be 309. I see 295. Yeah, can you download it? Okay, while you're downloading it, I think. Yeah, go ahead. It's tripped my CRC check, as you can see. Right? But basically, there are new technologies, 3D, monolithic 3D, for example, all of those are new technologies. There are also optical technologies, wireless technologies. I think these are actually interesting technologies to re-examine communication, both on-chip and off-chip. Okay, you got the right ones now. There you go. Okay, I'll handle it. Thanks. Good to know your slides. Okay, so I've showed this picture actually early on in the first lecture, if you remember this picture. One of the things that is happening with new workloads that are executing on GPUs is computation is clearly increasing, right? But there's also a lot of communication. So you can see this already happening partially in one of the largest companies. So if you look at NVIDIA, for example, they've been investing not only in the computation infrastructure, clearly, which is important. They've been investing in the memory infrastructure, which is HBM. And they have also been investing in the communication infrastructure. Yes. Oh, it's not. Okay, so. Okay, is that better? All good? Okay. Yeah, basically, you need to improve communication as well. And one of the reasons why I believe they actually need to improve the communication a whole lot is there's a lot of communication across the GPUs. And one of the reasons is because memory is not enough in a single GPU. You have HBM, which is actually quite small for the working sets that you need for training, for example. If you talk about training, the working sets are huge, and HBM is, let's say, 80 gigabytes, 120 gigabytes. And you really need to communicate data across all of these GPUs. And if you want to communicate data across a large unified memory across GPUs, you really need a good network. If you don't have something like the NVLink that they have, which is, I think, then it's very hard to communicate that data quick. Does that make sense? So let's really exercise a lot of the bottlenecks that we've been talking about in this course. In the end, you want to communicate data. If you actually don't communicate data, maybe your networking needs to change in a different way. This is a very compute-centric network, if you think about it. Okay, so there have been technology improvements clearly to improve the bandwidth of a single link, but they also do other improvements like architectural improvements. As we have seen, these are different topologies, actually. These were some of their initial topologies in 2016, as you can see. This kind of like a mesh network, a slightly different one. And then they've actually went to all-to-all connection within 8 GPUs over here. And then they actually decided to do 72 GPUs over here with some indirect routers over here. These kind of resemble what we have seen in the last lectures, right? And these are not new, clearly. These are old concepts. But as the scale of the workload evolves, they need better communication mechanisms. Okay, well, maybe there's a much better way of designing systems than doing this. Doing this meaning, really, if you actually have a much more memory-centric computing system, maybe these pictures will change more. We've also seen, actually, the importance of the network when we talked about processing near memory using Tesseract, for example, graph processing accelerator. That, the network over there across different, within the processors inside the logic layer, as well as across the processors, like 3D cubes or 3D stacked memory plus logic chips, it's actually very important for performance. And a lot of the optimizations that later work did was on that network. Okay, so this also, I think, points out that we really need to think what's happening across the stack when we design these networks. These are really slides that I've used in the first lecture, so we're going to get back to these slides. Okay, any questions? Now I'm going to give you an exploration into on-chip networks, because we've done some of this rethinking when I thought it was actually also really important to do this. When we were moving from, for example, single core to multi-core, right? There were people were designing multi-core systems, and there are a lot of questions that we tackled, for example, in this lecture about multi-core systems, how to handle interference, etc. But how do you design the network in a many-core system where cores are actually on the same chip is a good question. By the way, this actually increases with wafer scale. Maybe I didn't add the wafer scale technologies as part of the technology, but as you go to wafer scale, your technology, your network becomes even more important because you're within a wafer, and the efficiency of the network determines how well you can communicate across the entire wafer, right? Okay, so what is on-chip networks? Clearly, on-chip networks is a case of a special case of general communication networks. You have processing elements, and you have routers, and all of these reside on chip. They can connect cores, caches, memory controllers. And if you have, let's say, thousands of cores, probably buses and crossbars are not scalable, as we have discussed, right, in the last lecture. They could be packet switched, usually. Some common topology is 2D mesh, but remember, we discussed different topologies last time. Hierarchical rings are also employed a lot, actually, in on-chip networks today. So these are some examples. So at the time, we were actually looking at a lot of these things. Virtual channel buffering was common. This is actually something that we questioned, for example. But basically, if you look at an on-chip network, you primarily serve cache misses and memory requests, right? You have a multi-threaded application or multi-programmed application where the network really serves cache misses that come out of the processing element and routes those cache misses to the memory controller or maybe some other cache somewhere else in the on-chip, and then returns the results back. Of course, this includes a coherence request also. Don't forget about coherence. You don't just get the data, but you also need to get the permissions for the data. You also need to get the translations, for example, potentially if you have virtual memory. So there's a lot of stuff that may go on the network. Okay, so this is another picture. We've seen this like common thinking at the time, which is really complex buffered virtual channel networks. You've seen all of this earlier. That's why I'm skipping relatively quickly. And these systems are actually built. These are some example networks, 2D mesh network in Tyler. I've shown you this picture multiple times, actually. And not only one network, but there are multiple networks in general. For example, in Tyler, there were 4 packet switch networks and 1 circuit switch network. As you can see, some of them are for request packets. Some of them are, one of the networks is for request packets, cache requests. One of the networks is for response packets. This ensures that you don't have a high-level deadlock for example, a request delaying a reply. And if you have that sort of deadlock, that's not good. Then the network cannot make progress. But if you actually separate things into two networks, you ensure that requests don't delay replies, right? So that's one of the reasons to build this, of course. The other reason is to optimize things, because request packets are small. You just request things, right? It requires an address. It requires some coherence request, for example. Whereas response packets are usually large, right? Especially if you're getting a cache block. It could be 64 bytes. It could be 256 bytes. Now you can customize your networks to different data types that are demanded by the packets that you're, or the type of traffic that you're handling. So there are other networks over here that you can read more about this in their papers. And also we've discussed that they have a circuit switch networks, which is really good for transferring a lot of data from one node to another node. If you're streaming from one core to memory, or from memory to another core, for example, if you have a display traffic going from a GPU all the way to the graphics memory, then you may actually want to stream all of that huge amount of data through the network. And to be able to stream data, you can set up a connection across a path, and you don't change that connection because you don't really need to dynamically switch every single packet, which is much smaller than the amount of data that you may be streaming. You may be streaming gigabytes of data, for example. It doesn't make sense to actually make a routing decision at every router for every 64 bytes of that gigabyte of data, right? If you actually have circuit switch that you set up the path, and you don't need to make any dynamic decision anymore, that path is set up and you don't waste energy, and the performance can be also very high with optimizations. Okay, so again, I'm spending some more time, but hopefully this gives you an idea. Okay, so let's talk about on-chip a little bit, because we're going to deconstruct some of the things that are taken for granted. So you have some advantages and disadvantages when you go from on-chip to off-chip. Clearly, on-chip, you have low latency between cores. No pin constraints. That's a huge advantage, actually. When you go off-chip, you have to go through pins, which are expensive. And usually your area gets dominated by those pins. You have a lot of rich and low-power wiring resources. If you think about wiring on chip, we kind of don't even think about it sometimes, right? Especially on a compute-centric chip today. With memory chips today, as we have discussed, people don't think about wiring as, well, wiring is not as common because they're supposed to just supply the data, right? Whereas on a processor chip, you have wiring resources. You have multiple metal layers, maybe 14, 15 metal layers. So you can actually put a lot of wires on top of each other, right? With the memory-centric computing, I think that also needs to change, as we have discussed. You probably need more wiring resources, but let's not get over there. So on chip today, on compute-centric chips, you have a lot of wiring. As a result, you have very high bandwidth on chip. And if you have a lot of wiring, you can do better coordination. So contrast this with a supercomputer, for example, or whatever. All of these networks, laptops are connected to a network, right? Internet. If you think about it, the wiring is actually not plentiful on a supercomputer or the internet. Basically, you have wires. You have really physical, huge wires. Well, on chip, you have physical wires also, except we don't see them there a lot, right? Technology scaling has enabled us to reduce the size of those wires. Unfortunately, we don't have a similar technology scaling that has happened in the large scale, or at least outside the electronics domain. Physical wires are still here. And if you want to wire many of them, you run into a huge amount of complexity. And if you look at, for example, supercomputers, at least things, supercomputers that don't use optical networks, one of the big issues is really figuring out how to wire those different processors, right? And some of the bugs that have happened in supercomputers are because someone actually miswired a computer. So it's good to think about that, right? One of the benefits of optical technology is it gets rid of a lot of that overhead of wiring, right? You don't need to have physical wires. You need to communicate in the optical medium. Wireless is similar also. Okay, so if you, yeah, I've already said, you can do better global coordination across different cores if you actually have rich wiring resources that you can access with low latency. But of course, on-chip also has constraints. Now your substrate limits the ease to implement topologies. You have a two-dimensional substrate. Three-dimensional technology can change this, of course. But it's not as flexible as this wire, right? Here, I can move this wire anywhere. Whereas on-chip, I cannot do that, right? Not so easy. And energy and power consumption becomes a key concern also because you have a total power limit on chip because of the cooling constraints. And 3D doesn't help this. Actually, three-dimensional stacking doesn't help this. It makes it worse because heat cannot escape easily. As a result, if you want to employ very complex algorithms in your network, for example, this may be undesirable, right? Because it now you need to do more computation to actually enable those algorithms. Right? And that computation eats away from other computation that you may need to do. This is less of a concern if you have a dedicated router chip, for example, in a supercomputer. In a supercomputer, you have a processor, and then you have a router chip, and that router chip handles the communication, and that router chip's function is just to do routing, right? Or networking functions. A lot of those get integrated into the processor today, of course, right? Because of the success of technology scaling again and Moore's law. Okay, another thing that's undesirable on chip is large buffers, because buffers are what consume area and power, and we're going to tackle this. And in the end, the wiring resources, you actually have a lot of rich wiring resources because you have a lot of area, but whether you have enough area and whether you have enough metal layers constrain the use of your wiring resources. So very complex topologies that may require a lot of wires to go on top of each other, for example, may not be easy to implement on chip. But they may be easier to implement off chip, right? If you think about if you have a very complex topology where you require 50 wires to go on top of each other, well, you don't have enough wiring, enough layers of metal on chip because that's the technology that you're dealing with. But I can put 50 of these on top of each other. I can handle the complexity somehow, right? There's a way, basically. So these are the key differences, essentially. So there are other things that we can quickly discuss. So what is the cost? Where does cost come from off chip versus on chip? Essentially, off chip, it's channels, pins, connectors, cables. Whereas on chip, some of these are not that important because pins, for example, you don't go off chip. There's no pins, essentially. Cost is really on storage and switches. And this leads to networks with many white channels and less buffering, but still buffering. So channel characteristics, on chip, you have short distance, low latency. And essentially, you can also do other things on chip more easily. For example, put logic in repeaters, right? And workloads also are a little bit different. Off chip, usually you have large scale parallel application, multi-chip traffic, or some sort of distributed computation, right? As we discussed last time, or in one of the lectures, we can distribute computation on the network, right? Through message passing, etc., on the internet also. Essentially, that sort of traffic is a little bit different from multi-core and cache memory traffic. Okay, so applications are also different. So we're going to look at some of these trade-offs, but especially from the context of buffering and flow control. But if you're interested, there are a lot of papers in this area. This is one of the earliest papers from Bill Daly and his student, which talks about some of these, for example. If you read this paper, it talks about some of the interesting things. What topologies are best matched to the abundant wiring resource available on chip, for example. What flow control methods reduce buffer count and enhance router overhead? Which is an interesting question to ask. Even after this question was asked, let's say in 2001, a lot of people didn't think about it as deeply, in my opinion. So we'll see some more thinking on this direction. Okay, I'll not go through this, so you can read the paper. It'll be on your homework, I think. Okay, so there's more also on chip and off chip trade-offs. This is a paper that we published at SIGCOMM. This may still be the only on chip network paper on SIGCOMM. SIGCOMM is the major networking conference. And surprisingly, they have kind of limited themselves to outside a chip. So all networking for them goes outside the chip. But this is the only paper in my, well, I haven't checked every single proceeding recently, but that looked at some of the trade-offs between in on-chip networks versus off-chip networks. If you're interested, you can take a look at it. I'm going to mention that later quickly. Okay. Any questions? Yes. 28. 28. Where's 28? Okay, this one. Yes. Mm-hmm. Mm-hmm. Well, this is a specific type of deadlock that I mentioned. You have a requests to cache request, and then you have replies, which is data. You can think of this as control packets versus data packets. So one of the problems, there are a lot of issues related to deadlock. I think part of them were discussed in the last lecture. But one of the deadlock issues is higher level, protocol level deadlock, where a request packet may keep resources such that reply packets cannot go through. If you separate these networks, then you don't have that problem, right? Does that make sense? Yeah. I'm not suggesting every single deadlock will not occur, but at least that type of deadlock you don't need to deal with. And also there are other reasons to separate those networks. Okay. Okay. So let's examine one of these design choices. As I said, when architecture changes, when workloads change, when technology changes, maybe it's good to re-examine some of these resources. And by the way, this is actually a good way of thinking about research. If you're looking for a research problem, think about what is changing and what kind of implications that has on a particular important problem, right? In this case, we're talking about communication. And things are changing, for example, we're moving into memory-centric systems. How do we handle networking or communication in a memory-centric system, right? How do you handle interconnects? What kind of interconnects do we need? So it's good to ask those questions. This is a good way of actually thinking about research questions. Another way is technology, for example. I have this three-dimensional technology that's going to be very important 10 years down the road. What can I do with it? That can bring you some other things, other new ideas as well, right? So all of these things I said, workloads, architectures, technologies, as they change, they also bring about new research problems. Okay, so we tackled the issue of buffering because this was actually kind of bothering us. Basically, clearly we know that buffers are necessary for high network throughput. As you increase the buffers, you get better injection rates. So for a given, everything else being equal, and assuming your access pattern likes large injection rates, if you have large buffers, you'll get higher saturation throughput, essentially. If you have small buffers, your throughput will saturate early because you cannot inject enough things in the network. This is very intuitive, right? If you don't have enough buffers, at some point, the network will say, I don't have enough buffers, they'll stop injecting, right? Does that make sense? So buffers really determine the available capacity in the network. So buffers are good in that sense. But of course, buffers are bad in many other senses, especially in on-chip networks. They consume significant energy and power, dynamic energy when you read or write. They also consume static energy when they're not occupied. They also add complexity and latency, as we have discussed, especially in the last lecture, but earlier today also. You need logic for buffer management, virtual channel allocation, credit-based flow control, or some sort of flow control mechanism. So they require significant chip area, essentially. So there were actually multiple prototypes that were built that were large-scale chips, and this is one of them. I don't think it did buffering very efficiently, but because of that, the buffers occupied about 75% of the total on-chip network area. Maybe 75% is too much, but you can actually, buffers, depending on how much buffering you use and what kind of technology you use to implement your buffers, this could be 40% easily. Because you do need buffering, especially in large-scale networks, to tolerate the round-trip latencies, for example. Yes? This one? Yeah, potentially. Yeah, there's some slight difference over here, but I cannot really. Yes, this picture is not necessarily perfect. But I think there is actually that's a tougher one. Because if you have larger buffers, that may not necessarily need large latency, right? Depends on how you use the buffer, right? If you actually, for example, depend on what kind of operations you do on the buffer. If the operations are searching the buffer, yes. But if the operations are these FIFO buffers, if these are first in, first out, then that may not affect your latency as much. That's why we didn't change that latency over there. Does that make sense? Yeah. That's a good question. Okay, so basically the question we asked is, can we get rid of buffers? Again, this is another example where you examine an extreme, right? Everybody is doing, let's say, a lot of buffering. For us, we felt actually there was too much buffering and too much complexity. It's good to examine some extreme where you don't have any buffering and ask the question, what is going to happen if we actually get rid of buffers? Of course, there are intermediate points, and we're going to move to some more intermediate points from this extreme as research progresses, as you will see. Okay, so of course the question is now, how much throughput do we really lose? How is latency affected, etc. on applications? And up to what injection rates can we use this sort of bufferless routing? And are there realistic scenarios in which a network on chip operates at injection rates below that threshold? So can we achieve energy reduction? Can we reduce area and complexity? So this paper in ISCA 2009 answers those questions, some of them very optimistically. We're going to fix some of these things later on, as you will see. I think of this as kind of the radar paper. If you remember the radar paper, we said we're going to get rid of refresh as much as possible. But we're going to be a bit optimistic about it because we don't know exactly how things behave, like variable retention time, some things that can be later discovered, right? Okay, so basically it's not a new idea also. This is actually an old idea. This is a beautiful paper by Paul Baran on distributed communications networks. It was written in 1962. It actually talks about a lot of issues on distributed communications networks, including routing, including very low-level issues, technologies of the time in the 60s, which are very different from technologies of today, actually. And the idea is, don't buffer things. Meaning, if two packets come to the same router, and they need to take the same output port, like this, they contend with each other. Essentially, don't buffer one. So in a buffered network, what happens if two packets come to the same router and need to take the same output port? One of them gets buffered, right? And you send it in the next cycle, potentially, hopefully. But bufferless routing says if there's no productive direction available for a given packet, send it to somewhere it doesn't want to go. So these two things need to, both of them need to go over here, but one of them gets deflected. It doesn't get always deflected. For example, both of these packets may get to their destination, come closer to their destination, if one of them goes here and the other goes here, right? If the destination is over here, right? Does that make sense? So that's what the productive direction not available means. Basically, existing routers try to route the packets such that you always make progress toward your destination, meaning you always take a productive direction, productive output port. Hot potato routing, as it's initially discussed, says sometimes you can take the non-productive direction as well, meaning go far away from your destination. Does that make sense? And this leads to clearly non-minimal routing, meaning the number of hops from your source to destination is not what is minimal given your topology. You can take the scenic route. It could take longer to get there. But this way you can eliminate the buffers. That's one advantage. And maybe you don't get that much performance impact because this packet, now it goes to some other router, and then it goes to some other router, and then it goes to some other router, and hopefully it'll get to its destination by taking a longer route. Right? Okay, so this is called hot potato routing because essentially you can think of it as a hot potato route. Yeah, a packet is a hot potato. Nobody can hold it for too long. You cannot buffer it essentially. You send the hot potato to the next person. Right? We could actually play hot potato over here and let's see who gets burned. Who gets burned is the buffered router. Okay, so basically, hopefully we're going to get rid of a lot of this complexity. And as I said, this paper was a bit optimistic. We're going to hopefully go back to that later. Yes. Mm-hmm. Yes. That's right. Mm-hmm. Mm-hmm. Yeah. Mm-hmm. Yeah. So that's a good question. And the paper tackles two things. So if you do flit level routing, if you use wormhole routing, what you said is true. But you could also basically have a flit and treat it as essentially a packet, right? So the easiest way of implementing this is really having small flits, but treating them as packets, meaning having source and destination information over there as well. If you, the paper discusses a case where you still have header information and source and destination information only in the, let's say, what is this called? First header packet, essentially. But then you run into two worms hitting each other, and at some point you may need to break a worm. And that's not an easy thing to tackle. So for complexity reasons, we discussed that case and we actually say you can actually do it, but it's much more complex than actually doing treating each flit to be a packet. Okay, so here basically, yeah, essentially what we do is we replace the buffering and all of the buffer arbitration, etc., virtual channels with flit ranking and port prioritization. Essentially, we create a ranking over all incoming flits to the router. And for a given flit in this ranking, we find the best free output port, meaning this applies to each flit in order of ranking. Essentially, that's the router's job now. So a router does these two only. Okay, of course, these are not necessarily cheap. But essentially, each flit is routed independently. That answers your question. And, we do flit level routing. We do oldest first arbitration, which really guarantees live lock freedom, as we will discuss. Essentially, you have oldest first ranking when you rank the flits. You have some ages based on in each flit. And then you assign the flit to the productive port if possible. Otherwise, assign it to the non-productive port. Then the question, of course, can this be applied to any topology? Unfortunately, not every topology, but most topologies that are implemented today, meaning number of output ports. I don't know what's wrong with this, but number of output ports needs to be greater than equal to the number of input ports. If you have number of output ports less than number of output ports, then you have a problem, right? You don't have enough, in a sense, you don't have enough buffering. What's the definition of buffering here? You're really buffering packets on links right now. You're really using the links to buffer things, right? Okay. And every router needs to be reachable from every other router, of course. So now the flow control becomes completely local. Now, what does this mean? You don't need to check for buffer availability downstream. Right? That communication goes away. You can inject whenever the input port is free. You don't have any deadlocks. Every flit is always moving, right? Assuming your topology supports it. It should. Now you have the problem of live locks. And we're going to talk a lot more about that later on. You have the problem of live lock, meaning you misrouted or deflected a flit, and it may not reach its destination. Assuming you have oldest first ranking, and assuming every router obeys oldest first ranking, that's not a problem. Right? Oldest flit will always reach its destination, and then some other flit will become the oldest. Right? Okay. So clearly, this comes at advantages and disadvantages. We've covered a lot of these over here, so I'm not going to go through everything, but essentially, adaptivity is one advantage. Packets are deflected around congested areas. So you have some local congestion. You can actually tolerate that local congestion by deflecting the packets outside so that packets take longer routes. We discussed router latency reduction. I'm not going to talk about that. Clearly, there's area savings, but then there are disadvantages also. I think we've talked about this. There's also increased buffering at receiver, unfortunately, because now your flits don't necessarily arrive in order. Each flit is routed independently, and a packet, for example, like a cache a cache data packet, cache block packet, maybe 64 bytes. Each flit maybe 8 bytes, right? Now you need to reassemble all of that 64 bytes in the destination. So in the destination, you need to have buffers. As we will see in the later work, these buffers are already kind of there. These are misbuffers, right? When the processor requests a cache block, it really allocates space for 64 bytes, and it waits for those 64 bytes to come back. Clearly, oldest first arbitration is complex. We have header information in each flit. That's expensive compared to wormhole routing. So we need additional wires for header information. QoS becomes a little bit more difficult, but there needs to be more work in that area. Okay, so we did some evaluation, and this is with some synthetic traces, we get what we expect, meaning this is BLES, and this is the best baseline with some good routing, minimal adaptive routing over here. For uniform random injection rates, you get significantly reduced throughput. This doesn't sound like good news, right? If you just look at synthetic traffic. Now, some other workloads are actually not like this. Workloads are not always uniform random. They do caching, so you don't go to the network a lot. And we see basically good results on real workloads. So this was one of the other things that we wanted to convey in this paper. On real workloads, you may not need that much throughput. And later works actually kind of showed that as well. So we get basically very little workload, application level degradation. I don't want to go through this in detail, but that's how it is. But you'd get significant energy savings. So if you look at this picture over here, what should I look at over here? Essentially, these are the bufferless networks over here. We can reduce the buffer energy significantly. What increases, link energy actually increases, because now you have more links that are being traversed, right? Because you're actually using more of the link capacity. And the others actually are kind of similar, but they increase slightly. So because you reduce the buffering energy significantly, you have an overall significant energy savings. Hopefully that makes sense. Of course, this assumes if your buffers are a lot more optimized, these savings may be lower. So it really depends on what is your energy distribution across buffering, links, and routing. If your links are very expensive in terms of like width, for example, that also may not be very good, right? But then in the baseline, that may not be very good also, right? So it's good to think about that. So the savings you get really depend on where is energy spent. This is not an unreasonable picture actually over here. You get, this is other functions of the router, blue part. This is the link energy, and this is the buffer energy. Link energy may be a lot higher if your frequency is higher, for example, etc. Okay, so basically the takeaways over here is on real workloads, injection rates are not very high, and there are multiple reasons over here. One of the reasons is your caches have some effectiveness. You're not sending every single request, and also it depends on where you place the network, right? If your network is after L1 or after L2, it's good to think about. In this case, we look at after L1, and also after some point, the cores don't keep injecting. This is actually good to think about. Some of these access patterns say you keep injecting, meaning it's an open loop traffic. You keep injecting, and the cores keep injecting, and they can keep injecting forever. That's not real, in the sense that in a processor, you're running a real application, and that real application is using buffering resources inside the processor instruction window. And at some point, you run out of resources in the processor, and you cannot keep injecting into the network. Right? Does that make sense? You cannot sustain more than some number of cache misses. And we've discussed this issue also. Like Run Ahead, for example, tries to solve this problem when you're stalled. Essentially, at some point, the processor will stall. So the networks are really self-throttling. Okay, so basically, for bursts and temporary hotspots, you can use network links as buffers. Okay, these are the conclusions. I will not go through this, but essentially, our goal was to make a strong case for rethinking of network on chip design. And future research, this is what we envisioned. Any questions? Yes, please. Mm-hmm. Mm-hmm. Yes, I think this is basically you still need to have some pipeline buffers. Meaning there are different kinds of buffers, right? One is really buffering a packet that cannot go out. And then you still have pipelining in the router, right? And that pipelining requires some buffers. Does that make sense? So that's actually interesting. And that's a very good question. Some of the later works actually looked at using those pipeline buffers as also buffers. So it's good to think about that. You actually already have some buffers inside a router. Mm-hmm. Slight performance degradation. Yes, exactly. Mm-hmm. Exactly. Yes, exactly. So you get significant energy savings and area savings. But yes, performance slowdown, you incur some. But we're going to actually make this a lot more, let's say, detailed soon. Any questions? Okay. So of course, the question is always, can we do better? That's the question we asked. And also, we wanted to understand whether some of the things that we assumed were doable. And we will find out that some of the things are not as easy to do. But we can do better also. Okay, so basically, these are some of the major issues in bufferless deflection routing. You have live lock problem to solve. And we're going to talk about that. The good thing is you don't have a deadlock problem, right? We discussed deadlock, for example, in the last lecture. We discussed the turn model, which is a beautiful model for routing, etc. You don't need to deal with any of that with bufferless routing. But because of live lock, there's some actually resulting routing complexity that we have that needs to be taken into account. So we're going to go deeper into router design a little bit more. There's, of course, performance issues and congestion issues, especially at high loads. So the reason we didn't see a lot of performance degradation is because workloads were not really having high loads on the network. But on workloads where you have a lot of high injection rates, you will see a lot more performance degradation. And I'm going to show you some results. Again, the question is whether those workloads are realistic or not realistic. I don't know. I think this needs to be investigated depending on what your workloads are. But it's good to for a research paper to look at the entire spectrum. And then there's quality of service and fairness issues that I'm not going to talk a lot about. We're going to look at that in a different way. Okay, so this is the next paper, which tries to solve some of the issues. We call it chipper. I think I've kind of summarized things over here. These were the conclusions of the BLESS paper: energy savings, area reduction, and small performance loss. Unfortunately, we did not address some of the complexities in the router. And especially the live lock issue leads to long critical path, and we have large reassembly buffers. So we recognize especially the large reassembly buffers, and we said it's not a big problem, but we're going to look at some other issue over here at the protocol level. And the goal over here in this work was to obtain benefits as much as possible while simplifying the router to make bufferless NOCs more practical. So let's take a look at these problems. Essentially, we must provide live lock freedom, right? A packet should not be deflected forever, if you think about it. And you must reassemble packets on arrival. Essentially, you have a bunch of packets, and they arrive at a destination node, and they need to reassemble in some order. Okay, so this is the high-level view of a bufferless router. Essentially, this is the router. This is local node. In the router, you have some deflection routing logic, and then the crossbar, and then you inject, and then you eject. When you eject, meaning when the packet or flit reaches the destination, you put it into a reassembly buffer. And then, you serve it to the processor. So we're going to solve these issues. First problem is live lock freedom. The second problem is packet reassembly. These are at different points, as you can see. Okay. So live lock freedom is actually interesting. Essentially, well, I already said this. So the live lock freedom that originally that we thought, and a lot of people thought, was you need to sort the flits by age and then assign them in age order to output ports. This is called oldest first arbitration. It's thought to be complex, and in this paper we quantify the complexity of it. And essentially we find out that the router needs a much longer critical path than a buffered router to be able to do this, and we will see the reasons a little bit. And you also should reassemble packets upon arrival, and the number of buffers you have on the reassembly side or the destination side needs to be sized for the worst case. And worst case meaning, what is worst case? Every single node is sending something to the same destination. Right? So for example, for a small network, 64 nodes, 64 byte cache blocks, it could be 4 kilobyte per node. As network scales, of course, this also increases. Okay, you may think this is not that bad, and I agree, it's kind of not that bad, but some of the issue that we're going to discuss is not going to be just about the size of the buffers. Okay, let's talk about live lock freedom. So what stops a flit from deflecting forever? Essentially, you time step all flits, assuming everybody has the same time, which is also another problem, right? Synchronization. All the splits are assigned their desired ports, which means that all prior work imposed a total order among flits, and every router obeys that total order. The age of flits forms a total order, and you guarantee progress for the flit that has the oldest age. If a router sees that flit, it prioritizes that. If a router doesn't see that flit and it sees some other flit, it prioritizes the oldest one, essentially. Now, new traffic gets the lowest priority, of course, in the router. So what is the cost of this, essentially? So let's take a look at a little bit deeper. So we want to sort flits by age. This can be done using a sorting network. So if you think about a router, 4x4 router, it really is composed of these 3 levels of 2x2 routers. Right? You can think of it that way. And if you have 4 flits coming, and these are the priorities of the flits, the highest priority is 1, the lowest priority is 4, you need 3 comparator stages. Let's take a look at the first router over here. It basically compares 1 and 4. It says 1 is smaller than 4, so it's highest priority, so I'm going to push it up, let's say. And then the second router also does something like that. Okay, so this is your sorting network in the end. Okay, you can design the entire sorting network. Basically, what this does is it really, the goal is to compare things so that you get the ordering of the ages in order at the outputs. Make sense? Okay. You can design these. People have been designing this for a real long time. So these are expensive, essentially. This is clearly you have a sorting network that you need to do. On top of this, after sorting, you need to allocate flits to outputs in priority order. Now what we've done is just determine priorities, right? Which flit has higher priority. Now we need to allocate ports, essentially to flits that have higher priority should get their productive output ports. This means that younger flits, the ports that are assigned to younger flits, depend on what has happened to the older flits, right? So there's some sequential dependence in the port allocator. So let's take a look at that. So the first flit, the one that is determined to be the highest priority, oldest, requests east. Will it get east? Yes, because nobody else requested east so far. This is the highest priority. This is the job of the port allocator. Clearly, there's a circuit that does this, which means that only north, south, and west are available to the next priority flit. It requests also east. Too bad you don't have east. You get assigned north, and this happens to be a non-productive port, so you get deflected. Now, only south and west are available for the next priority. It requests south, so it's good. It gets to this productive output port. Only west is available for the poor last priority flit. If it requests west, it's lucky. If it doesn't, then it also gets deflected, as you can see. So now we deflected 2 flits, and we've granted productive ports to 2 flits. This could actually lead to not so optimal decisions also, as we will see later on. Okay, so this is the router that we kind of designed. You have a priority sort that determines which flits are which priority, and then you allocate the ports based on priority levels. And if you design something like this, you get a much longer critical path than a buffered router, state-of-the-art buffered router. Now, of course, you can say, I can do a lot of these things in parallel. Yes, absolutely. You can actually parallelize a lot of things. You can basically do speculative decisions, for example. You can make for example, this sequential dependence can be gotten rid of by saying, this is the port I would assign to the second flit, assuming I have north, south, west available. And then you also have southwest, east available. So you basically speculatively make multiple decisions. And based on what you actually assign to the first flit, you pick the one that is correct. Of course, this leads to some exponential dependence now, because you need to do more for 3, and you need to do more options for 4, right? Essentially, you need to do a lot of calculations. And this is only 4 inputs. If you actually have more inputs, then you have even bigger problem. Okay, so by actually adding more hardware, you can parallelize a lot of these. And this is another example of latency area trade-off, right? You can actually reduce latency a lot by adding more area. But we didn't want to do that necessarily. We wanted to actually solve the problem with live lock freedom in a more, like, let's say a creative way. So basically the question is there a cheaper way to route while guaranteeing live lock freedom? And the question, if you actually ask this question, then you really need to think, what is really necessary for live lock freedom in a network like this? Is oldest first really necessary? And the answer is basically yes. Well, oldest first is not necessary, so the answer is no. So basically with oldest first, you have a flit age that forms total order. Basically, key insight is you don't need that total order for live lock freedom. If your goal is to satisfy live lock freedom only, there is no need for total order. It's enough to pick one flit to prioritize until arrival. Basically, the whole network guarantee. You pick one flit and you call it the golden flit. And you say, I'm going to make sure that golden flit, after it's injected or after it becomes golden, gets delivered to its destination. So it gets prioritized everywhere in the network. And so you did that. That's good. And then if you ensure any flit is eventually picked, then you guarantee live lock freedom. Right? Hopefully this makes sense. And you don't need any age over here. You don't need to know when a flit is injected. You can just assign an arbitrary static ordering across all potential flits that could go into the network. That's the idea over here. Okay, so basically, which packet is golden? We select the golden packet so that a given packet stays golden long enough to ensure arrival, meaning maximum no contention latency, because this will be definitely prioritized by every single router in the network. And you need to ensure enough time for a packet to stay, or flit to stay golden, so that it reaches its destination, right? And then the selection rotates through all possible packet IDs, or you can think of it as fleet IDs. Essentially, we have a static rotation schedule for simplicity. Let's take a look at that. So you have a packet header, source, destination, and request ID. For example, starting from cycle 0, a potential request that goes from source 0 to request 0 is, So a potential request that is injected by source 0 and occupies request 0 slot. This is a request that could be injected by source 0 into the network. And source 0 may have 128 potential requests it could inject. We basically say at cycle 0, this is the golden one. We don't care if it's in the network. We don't care if source 0 is actually running anything. Does that make sense? So source 0 may not have injected anything over there, but it's golden. So the network will never encounter it. But this is simplicity, meaning every router knows that at cycle 0, this is the packet that's golden. And it will stay golden until cycle 100. At cycle 100, every router in the network says request 0, that's from source 1 is golden. This could be in the network, or may not be in the network, or maybe it will be injected later. We don't care again. If it's golden, it will be golden. Okay, and cycle 200, source 2, hopefully you get the idea, right? So you basically have a static rotation schedule for every source and every request. Now, this gives you a bound on live lock freedom. Hopefully, the worst case bound is not good, but the average case is actually quite good. And you can read the paper for more detail. Okay. So this is the minimum requirement again. We're kind of taking an extreme position over here, right? If there's another minimum, let me know. So now your routing decision becomes much simpler. You only need to properly route the golden flit. You don't care about an order. Essentially, the priority sort is gone, no need for full sort, and no need for sequential allocation. So let's route the golden flit in a 2-input router first. The first step is pick a winning flit. And the algorithm is, if this is what we want to achieve, if you have a golden flit, that's the winning flit. Otherwise, you randomly pick one flit to be to prioritize, meaning to be the winning flit. And then step 2 in the router, in this 2x2 router, is to steer the winning flit to its desired output port and deflect the other flit. Okay, this is a local decision over here. The router is going to be bigger, of course. This is a 2x2. We're going to do a 4x4 router. So a golden flit is always routed towards its destination. So this building block satisfies what we want to do. And it doesn't care about anything else. Everything else is random, right? Now, this is going to be a performance problem later on, as we will discuss, but maybe not too terrible. Okay, so now if you do golden flit routing with 4 inputs, each of these 2x2 routers will make a decision independently. So there's no dependence. So deflection becomes a distributed decision across these 2x2 routers. Let's take a look at an example. Assume that this yellow flit coming into the west input port is golden, and it's supposed to go over here. The red flit coming in the north input port is supposed to go over here. East input port, the green flit is supposed to go over here, and the blue one is supposed to go over here. Let's simulate what happens based on what I just described. So in this 2x2 router, you flip a coin because none of these is golden, and the red one happens to win. So red one, this router knows that red one's supposed to go over here, so it prioritizes the red one to go over that way. Now the green one still has a chance. That's the good part, right? Because even though it didn't win, it was lucky that it actually went to this part. Right? Okay. So here we know that this is golden, so it's still going to win. We're not going to actually flip a coin over here. It's going to win, meaning that it needs to go toward here, and the only way it can go toward here is if it gets this output port. So we're kind of having a router. We have a bigger network. This is really a network within a network, right? If you think about it. Okay, so the blue one is still also lucky. It can still reach its destination, right? Okay, now we go to the second stage. These are our inputs. These are our inputs over here. Let's take a look at the top router. We randomly flip a coin. The green one wins. So green one goes to its destination, productive destination, and blue one happens to also still have a productive destination. So they both are happy. That's good in this particular case. Here, the golden one wins. So it gets routed to its product output port, but the red one loses and it gets deflected. In this case, there was no other choice. So this case is a good case. Well, the red one would have been buffered, right? In a buffered network, the red one would have been buffered, but now it gets deflected, so it's going to take some longer route to its destination. Okay, now we've seen that these 2x2 routers can be completely independent, right? So there's no dependence. So that priority sort gets replaced. Actually, both of them get replaced. I've actually replaced the entire router for you. Make sense? Now you can design something 6x6, 8x8 if you have that big connectivity. Okay, so this is our permutation-based, network-based pipeline. We discussed the injection problem. We discussed the router. Essentially, now router is replaced. Actually, I don't have that picture. I guess I did have that picture over here. But this router is very simple right now. Now let's talk about the reassembly buffers. Any questions? Yes? No? Okay. Let's talk about reassembly buffers. Essentially, these buffers are large because in the worst case, every node needs to send a packet to one receiver. And if you think about n sending nodes, you need ON space in the receiver, right? And we cannot make reassembly buffers smaller because if it's too small, you can cause deadlock. Let's take a look at that issue. You can have many senders over here and not large enough reassembly buffer, let's say. Senders are sending to that receiver. And at some point, the green gets ejected to the receiver. And it's waiting for its pair, meaning the other packet, the other flit that is needed to reassemble the entire packet. Blue gets ejected. It's waiting for the other flit. Now, what may happen is you may inject those a bit later. The yellow one cannot get ejected over here because the reassembly buffer is full. So it's going to go around in the network. Have some fun in the network, let's say, right? But the senders are not throttled yet. They will send a lot of stuff. And if it so happens that these matching packets that are occupying the reassembly buffers over here, matching flits that are pairing the flits that are occupying the reassembly buffers over here, get injected too late, the network may become full. Basically, this is full. This is full, meaning all of the links are full with deflecting packets, terrible for energy also. And as a result, you cannot inject, so you're deadlocked. So for forward progress, these remaining flits must be injected, but there's no way to inject. So this is a higher level deadlock problem. You have, again, circular dependency on the buffers, right? And in this case, the circular dependency is not just on the buffers, but also in the network. Network becomes full. Okay. So that's why you cannot make them smaller. But we would like to ideally make them smaller. So how do you solve this problem? Clearly, there can be many solutions to this problem, right? You can drop whatever is in the network. You can communicate that you're really waiting for this. So we're going to talk about one solution. So one solution to avoid this sort of deadlock is have every sender to ask for permission. This is a conservative or very conservative solution, right? Whenever a sender wants to send a request, it asks permission. Do you have a reassembly buffer available for me? So you first reserve your slot. That's basically a control packet. And the receiver says, yes, I have one buffer available for you, so you can send me your flits. So you need to have an ACK. And then the sender sends. Clearly, this is not good for latency, right? Because it adds additional delay to every request. And this is, in general, very bad thing to do. This sort of conservative communication, meaning asking, do you have something available, is not good for latency, right? Because you're really adding inefficiency over a potentially very efficient network. Okay, so of course, the opposite is being optimistic. So this is conservative or pessimistic. So it can be optimistic also. You assume that there's a buffer available and you inject into the network. Right? That's the idea. And if it turns out this assumption was not true, the receiver drops the packet and says, sorry, I don't have something available, so send it again. Right? It's a negative acknowledgement. And then the sender retransmits. So now the sender sends two flits and they both get dropped, let's say. And the receiver next send a negative acknowledgement saying, I dropped your flits. It can tell exactly which flits, of course, because there'll be more than one flit probably. And then some other packet completes at some point, and space becomes available, and the center at some point retries. And when it retries, hopefully it'll get the space, but it's not guaranteed. It could be retrying many, many times, right? So this is retrying without having any information about buffer availability. Okay, and then at some point it gets an ACK, meaning only after it gets the ACK, it can deallocate these buffers. Right? Okay, sender frees the data. So okay, there's no additional delay in the best case. That's good in this, let's say, aggressive or optimistic approach. But now you have transmit buffering overhead for all packets, and also potentially many retransmits. You could be retransmitting many, many times, and you could get unlucky actually. It's very, basically, whether or not or when you will get a buffer slot now depends on what's happening, what else is happening in the network, right? Who else is freeing the buffer slots, etc. Who else is sending something? So there's a lot of retransmit traffic in this particular case. Okay, clearly I've given you two ends of the spectrum, and the solution lies somewhere in between. In this case, the one solution is to retransmit only when space becomes available. You're optimistic initially, and then you become pessimistic. But pessimism doesn't add additional delay because you communicate information between the sender and the receiver. Receiver knows that you tried to send, and receiver takes a record of it and says, when I have a buffer space available, I'm going to inform this guy whose packet I dropped. Make sense? That's the idea over here. So receiver drops the packet if the reassembly buffer is full and notes which packet it drops. And when space frees up, receiver reserves space, so the retransmit is successful. Now the receiver, of course, needs to do some bookkeeping in terms of what it has dropped. Right? That's the idea. Of course, you can actually add complexity and do more things. In this case, receiver notifies the sender to retransmit. Okay, let's take a look at this quickly, because hopefully you got the idea. The sender is optimistic to begin with. It sends its flit. The receiver drops it and takes a note. It doesn't negatively acknowledge yet, potentially. And then at some point, buffer space becomes available. And then at that point, the receiver says, I dropped your packets, but I did reserve a buffer for you, so please retransmit. Makes sense, right? And then once the sender retransmits, it will get the buffer. So there are no unnecessary retransmit except for the first one in this case. Yeah. Does that make sense? Any questions? Okay. Clearly, all of, yes. That's right, yes. Yeah. Yeah. Yes, but those are actually small because you're not keeping track of data, right? So that sort of buffering is small. You're really keeping track of some node ID, packet ID, or flit ID. So that's much smaller than a 64-byte or 256-byte cache block, right? Okay. And then clearly there's a family of policies that look like this, right? This is retransmit once, but you could do retransmit n times, potentially, right? And you can have different flavors, which I'm not going to talk about over here. Okay, and the other idea in this paper is really these buffers are already there. If you have a tight integration between the processor, assuming this is cache miss traffic, of course, or traffic that goes out to memory, right? Memory traffic in general. If you have a tight integration between the processor and the network design, you don't need to add additional buffers in the network because the processor needs to keep track of outstanding cache misses or any request that it puts out because it's waiting for it, right? It has to keep a record of it. It has to keep space for it. So these buffers are already there, essentially. So we use the MSHRs or miss status handling registers as buffers, as reassembly buffers. So basically you have reassembly buffering for free. It's really a truly bufferless network on chip. But of course, this requires the design of the basically the MSHRs together with the network. If you actually have separation, like if you're in a company where two parts don't talk to each other, somebody designs the MSHRs from the on-core, and then somebody else totally different, in a totally different department, designs the router, the router people will say, oh, I have buffers. So whatever comes to me, I have a buffer over here, right? And this buffer is clearly replicated actually somewhere else in a slightly different form maybe, but it's there. So there's a lot of redundancy that happens because there are different, let's say, groups doing different parts of the design. But now you've taken this course, you've seen some of these things may be more fluid maybe, right? It requires more communication, of course. Okay, so that's reassembly buffers essentially. Now we replace them with MIS buffers. So this is, in the end, I think this becomes a truly bufferless network because you really don't have reassembly buffers either. But you do need to manage the MIS buffers in the way that we have discussed. Okay, so that's the end. So that's the final. I'm going to show you some results and we're going to take a break. Now, we had the baseline bufferless deflection router, which had a long critical path because it was sorting by age. It was allocating ports sequentially. With golden packet and permutation network design, we replaced it with something much simpler. And we had the reassembly buffers. We had large buffers for the worst case. With retransmit once, we can reduce the size of those buffers with some additional bookkeeping. And now we can also use cache miss buffers, as network buffers. And in the end, this is what our router looks like. Now the question is how simple it is. So we evaluate it with actually very heavy workloads, as you will see soon, and different system configurations, etc. You can find more information. And we stress the interconnect as much as possible. If you actually have a perfect L2, it stresses the interconnect a lot, meaning the interconnect is between L1 and L2, and all of your traffic is actually within the L2. If you go to memory, that actually relaxes some of the traffic on the interconnect because some of your requests go to the memory controller and wait for hundreds of cycles. And that core at some point stalls, right? So you don't have as much traffic. Okay, so there's hardware modeling power that I'm not going to talk about in detail, but these are the results that we see. So for multi-thread applications, we don't see that much performance degradation. So this is buffered, this is blessed, this is chipper, because most of them actually are not that intensive, let's say. If you look at multi-programmed applications, the average performance degradation is about 13–14%. So you can see that it's worse than Bless. So Bless is actually more optimistic, but maybe not as easy to implement. In multi-thread, it's actually better. And on most workloads that are not as intensive, you have a small performance degradation. On workloads that are extremely intensive, you have a large performance degradation. So Stream, for example, is a very intensive workload. Almost every request is a cache miss. So you really flood the network over here. How realistic are they? It's good to ask the question, but there may be some workloads like this in real life too. Okay, so basically for low to medium intensity workloads, you get small loss, but for high intensity workloads, you have a large loss. Clearly, it depends. So power reduction is actually better than Bless. So Bless gets some power reduction. We get even more power reduction over here because of the router design. Router is much simpler right now. And also, I should say that the Bless evaluations are optimistic over here. They don't look at as much complexity in the router. Okay, I've already said that. So this is the router area compared to, again, buffered, we get significant area savings, similar to Bless, as you can see, but we save area a little bit more. The key improvement over Bless is the critical path base. Now we can reduce the critical path significantly. Clearly, this is a trade-off, as I said. You can actually reduce the critical path of Bless by increasing the router area significantly, but that's another design point. Okay. I will not talk about the conclusions because I already said all of these. But essentially, now frequency becomes comparable to buffered routers at much lower area and power cost, and minimal performance loss, especially on applications that don't stress the network. Any questions? Otherwise, we should take a break. Yes? Okay. Yes. Not more. Equal is enough. Yes, exactly. Yes, I mean, equality is enough, right? But if you have more, why not? Maybe. Depends on like what kind of communication you have. That's right. But equal is what we have today, right? In most workloads. If you look at a ring, it's equal. If you look at a mesh, it's equal. Okay. Okay, so let's take a break. Let's be back at, I think, 14:55. And then we're going to continue. We're going to ask the question, can we do better? And the answer will be yes. Okay, so let's continue. So now that we've improved upon the basic bufferless router, we're going to talk a little bit more about can we do better. And there are many aspects to it. And I think this research is not done yet. But I'm going to talk about a better router. And in the end, I think the realization is that completely bufferless is probably not that great. So we were at this extreme, right? Completely bufferless. If you really want to get higher performance, you need some amount of buffering. But maybe that buffering needs to be in a different way. And this paper introduced a different way of doing the buffering. Essentially, high deflection rate that you have hurts performance at high load, even though you get very good benefits in power and area. And the idea in this work actually introduces multiple techniques to bridge the gap between buffered and bufferless. Essentially, we're going to buffer some deflected flits. This is actually a different kind of buffering, right? Existing buffered routers buffer everything. Here, we're going to buffer only deflected flits, or otherwise to be deflected flits. I'm going to show you. And then we have some ejection bottleneck, as we will see, because you're bufferless, you have nowhere to take or ingest the things that want to get out of the network. And a particular flit may arrive to its destination, but multiple flits may arrive to that destination. And if you deflect one of them, that one of them actually goes around a lot more. So it creates more congestion. So if you actually increase the bandwidth to eject things from the network, you can be much more efficient and much higher performance. This doesn't affect the baseline network as much, but this affects the bufferless network a lot, because you're really putting a lot more pressure on the network. It's in a bufferless network when you have high load. And then we're going to talk about unnecessary deflections very quickly. I've kind of alluded to it. So you can actually have better prioritization. So in the end, this is actually much better than bufferless routers in terms of performance. So it really closes the half of the performance gap between buffered and bufferless. It puts you in a much better space while keeping the area and power benefits actually mostly, which is interesting. So there's still more work to be done to close that other gap. But actually some of the other works that I'm not going to talk about close that gap. Okay, let me talk about this a little bit more. We've already talked about a lot of this. We want to improve high load performance. So we talked about live lock, deadlock, protocol level deadlock at least. And now we're going to talk about high load, avoiding performance degradation at high load a little bit more. So essentially, there are multiple performance issues in a bufferless network. You have link contention. There's no buffers. And this is an extreme design choice. Any link contention causes a deflection. Right? So we're going to walk back on this extreme choice. But it was a choice that was really taken explicitly to say, okay, there's some space here that is not examined in research, right? So we're going to walk back to closer to buffered. We're going to talk about the ejection bottleneck, which happens because you can eject only one flit per router per cycle. And if you have simultaneous arrival of multiple flits to a destination, it causes deflection. And we're going to talk about deflection arbitration. Essentially, if you design a very fast arbiter, like we've discussed in the chipper work, it deflects things unnecessarily. So we're going to introduce a few ideas. A lot of them are actually quite simple once you know the problems. We're going to use side buffers. I'm going to talk about what that is. We're going to eject more flits per cycle, which is not going to affect complexity a lot, but it's going to buy you a lot of performance. And we're going to introduce a silver flit in addition to golden flit so that we don't deflect things. Again, this is another level of priority, right? We're walking, they're extremes, right? Oldest first may be considered one extreme. Golden flit may be considered another extreme for live lock freedom. And we add a little bit more prioritization. You can say, okay, add more prioritization. Now you'll get closer and closer to oldest first, right? Okay, so let's take a look at this. Essentially, buffering a flit can avoid deflection on contention, but if you actually buffer everything like in buffered networks, this is not good. This is what we were trying to eliminate, right? So the key idea in this work is to add a small buffer to a bufferless deflection router to buffer only flits that would have been deflected otherwise. That's the idea. So this is our baseline router. That's the bufferless router. Let's take a look at, you have two flits, red and blue. Red gets deflected for some reason, and blue, well, not for some reason, because of the way we designed the router. And the blue goes to its destination. So red one essentially gets deflected. So we're not going to deflect it. We're going to take it to a side buffer. And essentially, you can remove up to one deflected flit per cycle from the output ports and take it to the side buffer. And this is a FIFO, so it's a very simple buffer. But you can now, we're going to add a little bit to the injection pipeline so that we're going to inject from the side buffer as well. Not just from the local node, but also from the side buffer. This, you can think of this as a loop back, right? The deflected flit doesn't go anywhere else. It stays in this router, but it loops back and it gets reconsidered again. It gets a second chance. You can also think of it that way. Or maybe a third chance, and maybe a fourth chance. It could keep getting reflected, of course, right? That's the idea. So basically, you re-inject the split into the pipeline when a slot is available. Make sense? Okay. It adds a little bit more complexity, of course. Now you have a little bit buffering. You have a little bit more complexity over here in the injection. A lot of these you can hide with good design, let's say, but it is complexity in the end. Okay, so hopefully it won't get deflected the next time. But you can only hope. You can guarantee, if it becomes golden, you guarantee that it's not going to be deflected, of course, right? Okay. Okay, so I think essentially, relative to bufferless routers, you reduce the deflection rate. That's good. And we did some studies. If you have only a 4-flit buffer, deflection rate reduces by 39%. Clearly, you can add more buffering. And relative to buffered routers, buffer is much more efficiently used. You use the buffer only when it's really absolutely necessary. Right? Buffered routers essentially use buffers for everything. Right? And you can try to optimize that also. So you can basically get similar performance with 25% of the buffer space. Okay, let's talk about ejection. This again, relatively quickly, because it's a simple idea. Flits deflect unnecessarily because only one flit can eject per router per cycle. And we find that in 20% of all ejections, more than 2 flits could have ejected. Essentially, all but one flit must deflect and try again. And they cause additional contention. So if you actually make the ejection port bandwidth 2 flits per cycle, your deflection rate reduces by about 20%, which is not bad. Of course, you can make it 3, 4, 5, but then that adds more complexity. Okay, that's the idea. And I guess I don't need to animate this idea necessarily, but you have one ejection over here, and this guy, red one, even though it's at its destination router, it gets deflected, right? With side buffer, that's good. You can eject it better. But if you have dual ejection, well, if you have single with ejection, basically, it needs to come back at some point and try. Or it needs to come from the side buffer, but then that complicates this area a little bit also. Okay, if you have 2 ejection ports, both of them can be ejected consecutively or in parallel. Make sense? Okay. And for fair comparison, of course, you need to include this in the baseline routers as well, right? Now, the interesting thing is baseline routers don't benefit that much from the performance benefits of dual with ejection because they don't have as much of a problem, right? In the baseline router, if you actually have this problem, then you buffer things. Meaning the decision that you make in the baseline router is not as costly for performance, right? Here in bufferless routers, the cost is really congestion. No, sorry, not congestion, deflection. And if you think about deflection, you need to visit, depending on your topology. If your topology is a mesh, you need to visit 1, 2, 3 routers at least to get back to your destination, right? Does that make sense? I don't know if I made that calculation correctly, but 1, 2, 3, yeah, 3 routers at least, right? So a deflection is really costly, and this kind of not all deflections are equal in a sense. This is a kind of a terrible deflection. You reach your destination, now you're deflected because the destination cannot take you, right? That's the idea. Okay. Okay, and then there's a deflection arbitration. Basically, deflections sometimes occur unnecessarily because fast arbiters used simple priority schemes like we've discussed in Chipper. We don't want age-based priorities. We've discussed that already. And we've already discussed the state-of-the-art deflection arbitration, golden packet and two-stage permutation networks, right? So this random arbitration, if you don't have a golden packet, you randomly choose which one to prioritize, leads to actually not uncoordinated arbitration, meaning everything can get deflected because of this. If you actually put some coordination to this arbitration, meaning prioritize something else that's not golden, if the golden one doesn't exist, then you can actually get to a better decision. So we already discussed this earlier, right? Highest priority flit always routes to its destination, and golden packet is always the winning flit, right? I think we already discussed all of this. So let's take a look at how does lack of coordination cause unnecessary deflections. We have this red packet, its destination is here. Green packet, its destination is here. There's no flit that's golden, meaning all flits have equal priority. All of these routers will randomly pick one of the flits. So in this first stage, red flit wins. So it still has a chance, that's good. And blue flit goes there. Green flit loses at the first stage. Well, it already lost getting to its destination, right? Now it must be deflected. And in the second router, the random number is unlucky, let's say, which means that it chooses, basically it decides that green flit goes somewhere. Basically, it prioritizes the green flit, right? Red flit loses. So as a result, green flit goes to a destination, right? That red flit needs. So this happens because there is no real coordination. There's no prioritization in any of these routers. You basically have random decision making. So you could at least solve some of this by prioritizing one flit, right? So a golden flit, it's not present. Let's say there's a silver flit and at another priority level. Basically, ensure that at least one flit is not deflected in each cycle. Okay, we already discussed golden packet. Next highest priority is one silver flit per router per cycle. You can choose that pseudo-randomly again and locally to one router. Let's take a look at the idea, the same situation over here. Let's assume that there is no flit golden, but red flit is chosen as the silver one. So because there is no flit that's golden, red flit is guaranteed to go to the destination. So red flit wins at the first stage because it's prioritized because it's silver. This still happens to the green flit, unfortunately. And red flit reaches its destination, productive destination port. So at least one flit is not deflected. Now you can say, okay, I could make it more complicated, and yes. So you can certainly add more priority levels, right? You could actually have a second level priority or third level priority if you consider golden packet first level priority, which it is actually. And certainly you'll get a little bit more performance. Okay, so this is the minimally buffered deflection router. We solve the link contention problem using a side buffer now, or extra unnecessary deflections using the side buffer. We solve the extra unnecessary deflections due to the ejection bottleneck using dual width ejection. And we solve the unnecessary deflections due to the routing decisions that are made in the distributed arbitration mechanism by adding another level of priority. So clearly all of these lead to additional deflections, and we're trying to get rid of the deflections as much as possible. Okay. Make sense? So the paper is a lot of analysis. I'm not going to go through this in detail. And we compare to a lot of different routers, etc. I will mention one thing. There is also other work that was proposed after we published our original work. There's a hybrid bufferless and buffered router, which is interesting. It has both input buffers and deflection routing logic. So it performs coarse-grained switching, meaning sometimes you use deflection routing completely, sometimes you use buffered routing. Clearly, you pay the area cost of buffers and static energy, but you don't pay the dynamic energy cost. So it's a little bit more complex, but there's comparison to that also. So there could be other ideas also, if you think about it. Okay, so these are the results. Very quickly, all mechanisms individually reduce deflections because they're designed to reduce deflections. So you can see that these are the different deflection rates with different mechanisms. Nope. Yeah, so side buffer alone, if you look at this blue one, side buffer alone is not sufficient for performance. So weighted speed up higher is better over here, as you can see. And as you actually add more and more over here, you get better and better performance. And these are the deflection rates that we see in the end. So we start with about a 28% deflection rate, and we can reduce it down to 10%, which is interesting. And that improves performance. And this also clearly depends on workloads, but you can find the information in the paper. So these are the comparison points to other works, buffered routers. Clear their high performance over here. And here we classify the workloads based on the injection rates that they have in the networks. Clearly, the higher injection rate workloads, buffered routers win over here. But if you have small buffers, that's also not good, as you can see. The small buffer is sized to be the same as the side buffer that we introduced. So compared to the small buffer network, we actually do a little bit better on average, and better in workloads that inject a lot. Compared to a very heavily buffered network, we still have some gap, as you can see. But essentially, we kind of bridge half of the gap between the chipper and buffered, like heavily buffered networks. Okay. You can look at the numbers. It's exactly 2.7% somewhere. Okay. So there's more results that I'm not going to talk about, but I should probably say that, oh, okay, here I think actually I kind of assumed that buffered 4.1 was actually the same, but it actually has 4 virtual channels, I think. So we get similar performance to some buffered network with 25% buffering space. So we can reduce the buffering by 75% if you think about it at the same performance level. That's always good to also know. Okay, so I'm going to skip some of these results over here, but there's a lot of analysis. And buffer power is still much smaller and minimally buffered deflection network, even though we add a 4-flit buffer. So that's good. And there's more in the paper. Okay, I'm going to skip these because there's a lot of analysis. There's more analysis, which is the performance power spectrum over here, which is interesting. So clearly, if you do a design space exploration, you can vary the buffers that you have with different types of buffering. And at some point, your buffers are too many, so your performance improves very little, but your power increases, as you can see. So chipper is over here. This is the green one over here. And this is the min BD over here, which is actually not at a bad point, right? It's the lowest power network, but it has reasonable performance. So these energy efficiency, so in terms of energy efficiency, if you look at the performance per watt, this wins compared to other networks. But there's a more detailed analysis of this in the hierarchical rings paper that I'm not going to talk about. Okay, so clearly you can ask, what is the die area and critical path? This essentially affects the die area and the critical path a little bit compared to chipper, because we're adding more buffers clearly, right? But it's not that bad. Okay, so critical path increases, but I think we could optimize that better. So the critical path increases because you really are adding the stool with ejection and also side buffer, right? You need to consider new things to be both ejected as well as injected into the pipeline. Any questions? Now we got into the guts of router design a little bit more. Okay. So that's the paper. The question is always, can we do better? And I'm not going to go into a lot of detail on how we can do better, but I'll give you some basic ideas. So one of the issues is whenever you packet content in the network, you actually have congestion, right? And deflection happens. And once deflection happens, your load in the network increases even more. Because you don't want deflection. Deflection is really unnecessary usage of links. If you can reduce those deflections with minimum buffer deflection routing, that's good. But there's another way of reducing deflections, meaning don't inject into the network. Right? So if you can identify when you can get away with not injecting into the network sometimes, you can actually reduce the congestion in the network. And that's what this work does. Basically, the key idea of this work is really figure out which applications to throttle such that you can actually not congest the network too much. And this actually improves performance. And I'm not going to talk about it, but you get a significant performance and energy efficiency improvement compared to state-of-the-art throttling policies. I think it's very interesting, but it's going to be even more interesting if you combine this sort of idea with something else that I'm going to talk about. Hopefully, we will have time for that which is if you understand. So here, the throttling mechanism is really application level. Some applications are more sensitive to network. Some applications are less sensitive. If you're less sensitive, maybe you should be throttled more, right? Don't inject too much into the network. And usually the ones that are less sensitive, more sensitive need to, or less sensitive, have a lot of load on the network. Okay, so you can take a look at the paper. I will not go through this in detail, but there's more interesting things to be done in this area, I think. Last time we talked about hierarchical rings. I think combining topology and also flow control and buffering is actually very interesting, I think. So we developed methods for bufferless hierarchical rings, which is, I think, a very nice topology. In fact, if you actually design hierarchy into your topology, you reduce a lot of the overhead. So if you look at a non-hierarchical mesh network, it's not very scalable, right? So if you want to have, let's say, 100 by 100 mesh, the distance between one node that's over here and another node that's over here is a lot of hops, right? You can actually, it's 200 hops, right? In the best case. But if you actually rethink your topology such that it's more hierarchical, clearly you can have a hierarchy where you have a mesh, but then you concentrate, and let's say 100 nodes can be something else, right? Now you reduce the distance, clearly. But again, mesh has some issues in the sense that you only have local communication, right? And people have actually tried to eliminate that local communication. We did that, for example, with MEX network, multi-drop express channels. One of the downsides of mesh, it's very easy to lay out because it has only local communication. Every router communicates with the router that's next to it and nothing else, right? But it's also not scalable because of that, right? At least one of the reasons is that, because you, in terms of latency, it's not scalable because you have to go through every single router to get to your destination. Make sense? So one way of reducing that is to have communication that's more global. And that's what hierarchy enables, at least this sort of hierarchy enables. So if you look at this sort of hierarchy, this is a ring over here, clearly, and you have local communication between the red nodes. But if you have another ring that looks like this over here, you can communicate between these red nodes and these red nodes relatively fast, as opposed to compare this to having a single ring, of course, right? A single ring is not scalable also because you have to go through ON latency, where N is the number of nodes to reach your destination. Here we have partitioned the, well, not partitioned, but we've added hierarchy to the network, so you don't need to go ON, you really need to go OM, where really M is the number of partitions that you need to traverse. Make sense? Okay, so this sort of topology is very interesting as a result. And this is a paper that talks about it. Now, the good news is this is an area where it's very hard to have impact on industry, in my opinion, but industry has picked up these ideas. This is a very hard to read paper. If you're able to read it, they do actually something very similar to the hierarchical rings with deflection routing. Okay, so there are more papers over here that I'm not going to talk about, but I'd recommend people to take a look. Any questions? I'm going to switch gears a little bit. Yes. Yeah. What base? Could you say it again? Directory based. Yeah. Yeah. Yeah, that's a great question. Basically, if your interconnect looks like this or something else that is not bus based, right? If you're bus based, you can do snooping based protocols. If your interconnect is like this, now you don't have a single point of serialization physically, and as a result, snooping is very difficult to do. You could do it if you have a bus-based partition, right? So hierarchy can be such that a collection of processors, let's say 16 of them, are connected via bus. You could do snooping-based coherence over there, but once you go out of that domain, you need to do directory-based. So yes, basically the answer to your question is yes. A lot of the existing protocols are directory-based protocols, even though there may be a bus-based or snooping-based component to it, it's restricted to a very small fraction of the chip. That's a very good question. So clearly there's a design or co-design of the coherence protocol and interconnect as well. But I should also say that this may, if you think about it, snooping is a higher level choice. It's really, you can think of, so this is the physical implementation, right? This is how the network looks like. But snooping, the assumption of snooping is a virtual assumption, meaning it doesn't really require a physical bus. As long as you can guarantee with some other techniques that you can do snooping. Does that make sense? Now, clearly, snooping is easy on a shared medium. If you have a shared bus, you can snoop the bus and you can figure out who has the data and send invalidation automatically. You could do this on a network like this. It becomes much more complicated. You need to design a virtual snooping protocol that works on a non-shared medium. And there are papers on that. It's very complicated, but it's possible to do. Does that make sense? Yeah. So conceptually, snooping does not require a physical shared medium or shared interconnect. But for, let's say, simplicity, it's really good to have that shared medium. Yeah. Okay. Any other questions? Okay. Okay. Now let's jump into, there's more papers over here that I'm not going to talk about. I think I'm going to skip this one also. You can read it. So we've also looked at heterogeneous networks, and clearly we have some heterogeneous networks today. But I want to talk about packet scheduling a little bit, because I think this is an important topic. We're kind of switching gears over here. Clearly, you need to schedule packets in bufferless networks. We've kind of looked at that. But now we're going to look at packet scheduling at a higher level, meaning application level. Okay. So basically, what is packet scheduling? Essentially, a router needs to decide which packet to choose for a given output port. Right? And routers need to prioritize between competing flits. Which input port to choose, which virtual channel to choose, which applications packet to choose. And these are all questions to ask. We're assuming buffered over here, but again, that doesn't matter as much. There are common strategies that are used. For example, a lot of on-chip networks used to use round robin across virtual channels. Pick one virtual channel, in the next cycle, pick another virtual channel, etc. You do all this packet first, or an approximation of it, because it's expensive, as we've discussed. You prioritize some virtual channels over others, because that virtual channel may be carrying some important traffic, right, for quality of service. Basically, we want better policies in a multi-core environment. And we're going to use application characteristics. This will resemble some of the things that we have done with memory scheduling, as you will kind of see. And in the end, a lot of the scheduling problems are similar at some level. But maybe you'll need to consider the different parts of the system where you're implementing them. Okay, so we're going to talk about application-aware packet scheduling. So this is a higher level abstraction of the problem. You have a bunch of applications running, and you have network on chip, which is a critical resource shared across multiple applications. So the problem is packet scheduling, essentially. I'll skip through this. We're assuming a buffered router, but that doesn't matter as much over here. So the conceptual view is you have a bunch of virtual channels over here at different ports, including the processing element that is connected to this router. And let's assume that you have a bunch of applications. The scheduler task is to choose for each output virtual channel one input. The question is which packet to choose, right? So you could do round robin based, you could do age based. The problem with a lot of these policies is they're local to a router. Now, what does this mean? This is kind of what you've seen earlier, right, when we talked about memory scheduling. Memory scheduler does some decision, and it doesn't consider what the core does. Here, it's also similar. One router makes one decision, and one router may decide to prioritize a packet, and another router may decide to deprioritize it. And these routers may actually make contradictory decisions. So packets from one application may be prioritized by one router, only to be delayed at next. And if all routers are uncoordinated, which is the case in many systems, you could actually be making a lot of suboptimal decisions. And these decisions actually become worse as the network size scales. So that was one of the things that we wanted to solve. The other problem is this is application oblivious. So you treat all applications packets equally. And the problem is applications are very heterogeneous, as we already know by now very well. So the solution that we're going to look at is really application-aware global scheduling policies. And you could do this in on-chip networks more easily because you have you're restrained to only a single chip, right? You don't go outside and make these decisions outside. It becomes harder to do it outside. Of course, if your applications span many chips, then you're back to the same problem. But if you handle it nicely within a chip, maybe the problem is reduced globally also. Okay, so I'm going to give you an example of this sort of, we call it stall time critical scheduling example. So assume that this is the packet injection order at the processor. We're going to look at 3 cores, core 1, core 2, core 3. And this is time step, which cycle the packets are injected at. And we're going to do some batch-based scheduling that I'm not going to talk about in detail. We did that at PARBS, if you remember, so it's similar over here. We're going to consider 3 batches over here. And we're going to rank the threads based on some order over here. So you remember PARBS, you can apply the same principles over here in a simpler way, I would say. So let's take a look at how a round-robin scheduler would schedule these packets. It would basically, okay, what's a round-robin scheduler? You basically take packets from applications in a round-robin way, right? So, well, sorry, not applications, input ports in a round-robin way. Basically, you go round-robin across different virtual channels. So you take packet 5 from first virtual channel, second virtual channel, third one, fourth one, etc. So clearly, this is not aware of the applications at all, right? An application may be not so intensive and may want to be prioritized, right? So these are the stall cycles that you would get, assuming if you consider only this router. The paper has analysis for more routers. So if you do round-robin scheduling, essentially, these are the stall cycles that you would get. The red one finishes its requests after 11 cycles. The blue one finishes after 6 cycles. The green one after 2 cycles. No, sorry, 8 cycles, sorry. This is time from left to right. Okay, I think I got it right. 8 cycles. So the average is 8.3. Now, if you do age-based scheduling, you happen to be better over here. So you basically prioritize the packets that have the oldest age, meaning the lowest injection cycles, right? You basically first pick 1 over here, and then you pick 2. Okay, since everything is marked based on its injection cycle, it looks nicer, as you can see. And the stall cycles reduce, or happen to reduce in this case. They don't have to reduce necessarily, which is good. But if you're application aware, and if you rank the applications, and if you obey the ranking order at every router, then you can actually do much better. So that's the idea over here. You form a ranking order, and that ranking order gets broadcast to routers, and every router obeys the same ranking order. Now, if you do that, this router prioritizes the green applications packet, which is good for that green application because that green application didn't inject a lot of packets, meaning if you actually take out its packets quickly, hopefully it'll make faster progress. Similarly to the principles that we have for memory scheduling, right? Then the blue application, which is less, a little bit more intensive, but much less intensive than the red application, gets prioritized, and then the red application gets prioritized. You can see that the average stall cycles is much lower over here. I'm going through this relatively quickly because we've seen parallelism over batch scheduling, for example, and the principles here are relatively similar, except the decision needs to be coordinated across routers. So in this case, this router will reduce the stall time of average stall time of applications, but also other routers will do the same thing. Now, what enables this is really, you can coordinate this ranking across routers. For this to work, you need to have a way of communicating the ranking, computing the ranking. That's why we do batching. For a given batch, you compute a ranking, and that ranking needs to be coordinated across all of the routers. So there is a central structure that actually computes this ranking and communicates it to all of the routers, which is the least nice part of this work. But it is possible to do for an on-chip network. Once you go off chip, it's good to forget about it probably, because that's a lot of communication. But within chip, you have a lot of resources, and you can dedicate some of those resources to compute this ranking and enforce this ranking. Does that make sense? Okay. Okay, so there's a lot of evaluation in the paper. You can take a look at it. I like this sort of work because it really considers application awareness into the network. So if you look at a lot of the work in networking, a lot of them were based in the past on synthetic traffic. I input these synthetic traffics, and as a result, I get this performance, right? Which is okay from a network perspective, but not so great from an application perspective, right? But in the end, what we really need to evaluate the network, not just the network, actually, the entire system is really from an application perspective. What kind of application performance do we get? Okay. Now I'm going to give you another example of prioritization that takes into account application characteristics, and that's Slack. And this is also a general concept. So we've talked about application-aware prioritization. Clearly, this is a very general concept, right? You could do this in the network, you could do this in the memory controller, you could do this in the storage controller. And in the end, I think all of these concepts need to be coordinated across all of those controllers, right? Because your network may do something, and then your memory controller may do something completely different. As a result, you have a suboptimal performance. Slack is another concept that's actually very general. And I think we need to think more about Slack going into the future. Because it really can enable you to focus policies on things that really matter. Here, if you think about it, maybe some applications matter more than others, right? And we've already discussed that many times. But even within an application, some things matter more than others. Some things are more critical, some things are less critical. And we've also already seen that concept as well, right? When we talk about bottleneck acceleration, right? We said we have some critical path in a multi-threaded application. If we can predict that and prioritize it in some way by, for example, shipping the critical path to large cores, we can get better performance. So we're going to kind of use a similar idea. I think slack and criticality are two sides of the same coin. If something is not critical, that means it has some slack, meaning you can delay it in some way. If something is critical, probably you cannot delay it, right? Probably it has zero slack. Okay. So now we're going to look at this packet slack because we're looking at it from the perspective of the network. So actually, I should, before I go, the same thing exists in a memory controller also, right? So some requests, for example, may be critical because they're blocking the window. Some requests may not be critical because their latency is overlapped and they're not blocking the window, and their latency will be hidden, even if you don't. Even if you prioritize them, it's not going to buy you any performance, right? So we're going to take advantage of that notion of slack. Okay, so what is the slack of packet? In this case, slack of a packet is the number of cycles that can be delayed in a router without significantly reducing application's performance. Now, if you knew this information, or if you could calculate this information, or if you could estimate this information, you could design your routing policy to prioritize packets that don't have any slack. We call it local network slack because this is a local metric at that point in time for a particular packet, right? There's also a global slack, which is if you look at the entire application, but we're not going to talk about that in this particular work. So why is there slack? Basically, whatever we discussed in earlier lectures, because there are latency tolerance mechanisms. There's memory level parallelism. There are multiple requests outstanding, for example, from an application. And one of them may be long latency, the other may be short latency. And the short latency one probably has a lot of slack. Essentially, latency of an application's packet is hidden from the application due to overlap with latency of pending cache miss requests or other long latency operations. This is a long way of saying what I just said. So the key idea of slack-based scheduling is to estimate the slack of each packet, which may not be perfect, as we will see, and then prioritize the packets with lower slack. So I think I've already said all of this. So let's take a look at what is the concept of the slack. So if you look at the instruction window of a core, this is the core, and it's going to try to access this. I don't know, it could be a memory controller. It could be L2 cache over here, L2 cache block, or L2 cache slice that's on this part of the network. So this load miss causes some communication on the network that looks like this. This other load miss, blue one, happens to access a cache block that's over here. Clearly, this is shorter. And it finishes while the other cache miss is ongoing, right? So if you look at this, the blue one's latency is hidden, right? That makes sense. And you can compute its slack exactly assuming you know all of this. So the latency of the green one minus latency of the blue one gives you the slack of the blue one. Make sense? So you have a 20 hop latency slack. And you can delay that blue one maybe for some time. This doesn't take into account, of course, dependencies, etc., in the application. It's approximate. If you really want to look at the slack in terms of a performance impact perspective on the application, then you need to do a lot more than this. But this is the network slack. Does that make sense? Okay, so if you're just looking at from the network. Okay, so that's the slack. Now let's take a look at how we can take advantage of this. This is the exact same application that I showed, core A. And let's take a look at core B over here. Well, I guess it's a bit different over here. Yeah. In this case, packet, the similar application, I shouldn't say the exact application. Green packet has a slack of 0 hops, and blue packet has a slack of 10 hops. The other application does something that looks like this. It has an orange packet and a pink packet. An orange packet has a slack of 0 hops, but the red packet has a slack of 6 hops. Okay? Now you can see that there's some contention in these routers. The question is, once you have a contention in these routers, which one do you prioritize? We know that the slack of the red one is greater than the slack of the green one, so prioritize the green one. Make sense? Of course, now you can actually be smarter and compute how much slack is left once you delay things. So if you can have an accurate estimation of the slack, every router can get supplied that information along with the packet. So when you inject a packet to the network, if you can guess what kind of slack it will have, you can put that information to the header of the packet. And whenever it gets delayed because some other thing is prioritized, you can actually update that slack. Right? And the paper has a lot more detail that I'm not going to talk about over here. But actually, these are the slack in real applications. This is slack in cycles on the x-axis, and this is the percentage of all packets over here. So for example, for this application, 50% of packets have a very large number of slack cycles. And the reason for that is you have large memory latencies. Basically, some requests go and wait in the memory controller, and they're the ones that are really bottlenecking the application. And some requests sit in the caches, and their latencies are mostly overlapped. So prioritizing those requests from the application that are actually inside the network, and they're not going to go to the memory controller. They're going to be serviced from an L2 cache, for example, or an L3 cache. Does not make a lot of sense if you have something more important to prioritize. Right? So that's the idea over here. So you can see that a small fraction of packets have smaller slack cycles, but still significant. So you can actually identify things as critical versus non-critical based on the slack. That's one definition of criticality. So you can see that there are other applications. Different applications are different. So for this application, a very large number of packets have 0 slack cycles, which is interesting. And there's a huge variation across different applications we have examined. Okay, so slack varies between packets of different applications and also within a single application. Okay, so the question is, how do you estimate a priority level based on slack? So I will not go into a lot of detail because you do need to do a lot of prediction to be able to do that. So we're going to define slack as the maximum, for a packet. This is the slack of a packet. And we know what packets we've injected from a given core. And we kind of have an estimate of the latency of P. Right? So we're going to estimate both. The first one is maximum latency of P's predecessors, all of the packets that you've injected so far. You have an estimate of that. And then you have an estimate of the latency, and you do this computation. Hopefully that makes sense, right? We're looking at cache miss traffic. That's why this is outstanding cache miss request when P is issued. So the problem is packet latencies are not known when you're issued, right? So you need to predict the latency of any packet, Q. You have higher latency if Q is an L2 miss, because now you go to the memory controller. We're assuming a network where L1 cache misses go on the network, go to the appropriate L2 cache slice somewhere in the network. And then if it misses in the L2 cache, it goes to a memory controller. There's still communication from the L2 cache slice to the appropriate memory controller, but now the expectation is that you're going to wait for a long time in the memory controller. Right? All of these become much more complicated if you have prefetching, etc. So it's good to think about this. So you have higher latency if Q has to travel farther number of hops, of course. So I'll give you the basic idea. So what we do is this predicted L2 miss is set if any predecessor packet is servicing an L2 miss. But you may not know that again. You may not know that information unless there's communication that has happened from the destination L2 cache slice to the processor back. So you need to predict whether something is an L2 miss. So this is an area where predicting whether you will have an L2 miss will help. If you remember an earlier lecture, we talked about Hermes, right? Whether something will become an L2 miss. Now you can connect some of these concepts, right? So there are other benefits to predicting whether you'll get an L2 miss. Okay, so that's the latency of P. And so this my L2 is set if P is not servicing an L2 miss. You can read the paper for more detail. And essentially, we have a hop estimate that's maximum number of hops of predecessors minus the hops of P. So this is simplistic, but the results show that it works reasonably. So how do you predict whether you get an L2 hit or miss at the core? We have an L2 miss predictor, but we have a better one with Hermes today. So maybe this needs to be done better. And it's a threshold-based L2 miss predictor that I'm not going to talk about. You can find. And you compute the number of miss predecessors by using a list of outstanding L2 misses. And we do the hop estimate using essentially assuming XY routing in this case. So we're very simplistic in our estimation, but even simplistic estimation actually provides better performance. I'll give you very quickly the performance results. This is across a bunch of applications. I don't remember how many. Okay, let's go through this. Shortest job first is essentially what we've discussed earlier. We call this shortest job first, which is application-aware scheduling. So that provides performance improvement, and we knew that. If you actually do slack-based packet scheduling, by itself, it's better than shortest job first with slightly less complexity, arguably. If you actually combine both of these ideas, application-aware scheduling as well as Slack, you actually improve performance even more. And the comparison points are age-based scheduling, round-robin, and some other work at the time. So we also look at unfairness, and this reduces unfairness as well. Basically, shortest job first actually doesn't help unfairness, but actually if you do Slack-based scheduling, you help unfairness as well, because if you take into account Slack, you're making much more informed decisions. And this informed decision is hopefully not delaying things unnecessarily. Right? So if you actually make the right decision of Slack, right prediction of Slack, you should not be delaying things that are not supposed to be delayed. You should really strictly be reducing the slowdowns. Right? And that's what's happening actually, as we see. That's not true for shortest job first. If you actually do shortest job first, which is prioritizing applications that are less intensive, then that's not good for unfairness actually overall. Well, I guess actually compared to the baseline, it's still better, but not that much better. Okay. Okay, so I wanted to discuss this idea because this is another idea that's actually very generally applicable. And when we design our systems, we should probably be thinking more of Slack and criticality. Think about like these, maybe. Okay, any questions? No questions? Otherwise, I'll keep going. Okay, there's more work that I'm not going to talk about over here that are actually really interesting, but we don't have time. Let me give you one more thing, because I'll do this very quickly. I don't want to go through a lot of detail, but this is also another example where rethinking how to design a network such that you can actually optimize for a very large scale network and constraints like quality of service is going to be more important. So hopefully people will kind of, I think everything that I discussed today is really rethinking how you would design the network, right? You need to design a large scale network. You have on-chip constraints and you're not off-chip constrained with off-chip anymore. How do I rethink the network? Right? We're going to give another example of this over here. So basically our goal in this work was to really think about many, many agents in the near future. So we have a bunch of things, cores, accelerators, network on chip. And this is going to scale. And this is actually true, especially in wafer scale processors today. You have a lot of agents. But even in a GPU, you have actually a lot of agents today that communicate with each other. Also in CPUs, maybe not thousands in CPUs yet, because some of the CPUs are quite complex, right? Or cores. So we wanted to actually have a network that has high efficiency, and good performance and strong quality of service guarantees. So this was actually a big constraint for us. So the idea over here is actually interesting because we design a topology that provides quality of service. So the problem is if you want to actually provide quality of service, you can do it in each router. Each router may be providing some sort of quality of service to different flows or different applications. And this leads to increase in buffering, arbitration, and bookkeeping. So we actually did work on that I'm not going to talk about. And in the end, the result was more complexity. Although you get good quality of service, you get more complexity also. So we wanted to actually provide quality of service guarantees at low area and power cost. And the idea is to rethink how you actually handle shared resources. Basically, don't make everything shared or don't distribute your shared resources everywhere. Isolate them in a region of the network and support quality of service only in the routers within that area. You still have a network of connectivity between those shared resources, so your routers need to support quality of service. But outside of the network, you don't need to, outside of that shared region area, you don't need to support quality of service. But now the question becomes, how do you access that region with quality of service? So we designed the topology so that applications can access the region without interference from other applications. That's where the topology design comes in. So this is a pictorial example. One picture is worth 1,000 words, probably. This is the baseline. All routers are quality of service enabled. And you may have multiple virtual machines. For example, the virtual machine 1 is allocated these cores over here, 8 cores over here, and there's some concentration over here. 4 cores are connected through direct links, for example, or through a bus, for example. But everything is quality of service aware over here in the routers, for example. And the shared resources are everywhere. I don't know why the shared resources don't show up, but fine. Okay, I'll go through this relatively quickly. So essentially, whenever you're accessing a shared resource, these are the shared resources over here, you have a memory access. And you may contend across different virtual machines, or you can consider these as different applications. We were looking at the virtual machines over here. So clearly, this leads to a quality of service issue. So we wanted to really have network-wide guarantees without network-wide quality of service support. So if you have something like this, then you need to support quality of service in all of the routers, because your network is really not designed to provide some sort of isolation. This virtual machine tries to access the shared resource, but it has no way of accessing that shared resource by going through another virtual machine's resources, let's say, or another virtual machine's physical nodes. As a result, all of the nodes need to provide some sort of, all of the routers everywhere need to provide some sort of quality of service. Does that make sense? And we wanted to reduce that. Okay, so basic insight over here is to leverage rich network connectivity, which naturally reduces interference among flows. And this also limits the extent of hardware quality of service support. But of course, this requires a low diameter topology like we've discussed in the last lecture. Multi-drop express channels is one of them. You can think of these as express links, right? You go from this or this part of the network to this part of the network with a single link. And that single link has multiple drops over here. But if you go through the single link all the way over here, you don't have any interference. Okay, that's the idea. So that's the multi-drop express channels topology that gives you some isolation, meaning you're going through from here to here with a single link. Okay? So you can have other single links that look like this. And if you actually complete the topology, you actually have a lot of rich connectivity that has direct connections. Okay, and that's the router, which I'm not going to go into. So this is actually one-to-many topology. It has a low diameter, 2 hops maximum. Yeah, it's asymmetric. So there's arbitration complexity, etc. I'm not going to go through this because we discussed this. You discussed this last time, right, Mohammed? Maybe a little bit. But we don't have a lot of time also, so you can read it. But you can see that the key, what this enables is really an express link from this part of the network, which could have many routers. It could be a network within a network, as we discussed, to this part of the network. And these sort of express links are really important for both reducing latency as well as providing isolation, as we will see. Of course, the cons are there's some increased arbitration complexity because you can have multiple drops over here. And you need to also decide, as you can see, this is a richly connected network. You need to decide which link to send your request in. Okay, so this is the idea that I wanted to discuss. Basically, we dedicate quality resources or shared resources are actually constrained to some parts of the network. We call these dedicated quality of service enabled regions. So whenever you actually reach this part, and if you want to access a shared resource that may be somewhere over here, you get quality of service in your routers. So your routers here are very expensive, potentially. Right? So the rest of the die is really quality of service free. So you reduce some cost over here. Now the question is, how do you get from this part of the die to the shared resources? And the idea is really to use this richly connected topology to enable traffic isolation. Essentially, this sort of network, like multi-drop express channels, gives you the ability to reach this part, this quality of service enabled region from any part with isolation. You just send a request from this express link, if you will. That's the idea, basically. You use the topology of the network to provide traffic isolation. And this way, this virtual machine can access this quality of service enabled region directly, while this other virtual machine is also accessing this quality of service enabled region. Make sense? Okay, and there's no interference between them. Similarly, this virtual machine can communicate with this virtual machine internally, but now there could be interference over here. So you can still use these routers, but if you use these routers to communicate, for example, some of your cores are allocated over here, some of your cores are allocated over here because you're running a big virtual machine, let's say, and your resource manager did not do a good job, or it didn't have any option, right? Because it's allocating, it's using some allocation algorithm. This application may need to communicate with this other part of the application over here. So you can do this. But if you really want quality of service in that communication, you can do this. Make sense? So you take a longer path, but you actually can go through quality of service enabled routers. You get isolation here, you get isolation here, and you get good quality of service management over here. Does that make sense? So this is actually interesting. This is something that has not been enabled in many systems. Okay, so I will not go through the details of evaluation because there's a lot involved over here. Actually, there are more ideas over here than just the idea that I mentioned, but those require, I think, a little bit more background and thinking. For example, we do low power links, and we use low power links, but you can read the paper for more detail. But in the end, let me see. You get significant energy and performance benefits and with lower area compared to a quality of service enabled route or entire quality of service enabled network. And that's the summary. Okay. Since we've gone over time, we have very little time. You can ask questions. Any thoughts? We've covered a lot of concepts over here, but I wanted to push this topology design for, let's say, good quality of service as an example also. Because topologies are usually designed for performance, and we've seen a lot of that. It's good to think about some other metrics as well, especially if you really want to scale to a very large number of nodes. Having complicated routers in all parts of your network is probably not a good idea. Any questions, thoughts? Okay, I think people are tired. It's also very dark. Okay, we're done, so I'll see you tomorrow.